It is terrible, Valerie. I wasn't exaggerating. Yes, I do have access, but it was so like, why would you ruin it? Like before, I had a ruler down there that I could make straight lines with. It was so easy, and that why why give me an update that's worse than what I had before? I know people are going to be like, "Oh my!" Sometimes that happens. I just start with a rant. So today we are talking about completing the square. Completing the square is just another way to solve quadratic equations, which makes sense considering what we have been working on is quadratic equations, right? I know we took a little detour into complex numbers, and that is because we need to know how to use them as we move along in quadratic equations. But right now we're back to solving them. Today, the method we're using is completing the square. Um, the whole idea of completing the square is to create what we call perfect square trinomials. Now, if I have a perfect square trinomial, say I have x squared plus 14x plus 49, this would be considered a perfect square trinomial. And you aren't going to have to figure out what they are because you're going to be creating them yourself. And ultimately, what it's saying is if I have a perfect square here and I have a perfect square here, and I multiply, call this A, we call this B. If I have 2 times A, B in here. So if I have like the square root of this times the square root of this, right? So the square root of this is 7, square root of this is x. So 7 times x times 2 would make my middle portion. Do you need to know all that? No. What you need to know is that when you have a perfect square trinomial, it can be rewritten in its factored form as x plus 7 squared. And that's the whole reason we're doing this, is because if I can create a perfect square on one side, I can take the square root of both sides to solve it. I'm not spending a lot of time on what perfect square trinomials are because it's kind of an algebra 1 thing and it would take me a while to get into all of that. Um, but ultimately, you're going to be creating them, right? Um, and the reason you're going to be creating them, as I said, was for the purpose of solving them. Now, this is just a special formula that tells me that when I have a perfect square here and a perfect square here, and then 2 times those together right here, you could factor this, right? I mean, we've done that before. We've been doing factors. You could take, oh, well, I've got 49. And I go, well, it's 1 times 49 and it's 2 times whatever, 3 times whatever. But we all know that it's 7 times 7, right? And I'm looking for the ones that add up to that middle term, right? Which we would know would be 7 times 7. So we could go that, well, this is x plus 7 times x plus 7. So you can kind of see it in the factoring. The whole reason for doing it is when I get this in an equation form, I can use it to solve. So if I had x squared, same thing, plus 14x plus 49, and I say had it set equal to 4, right? I could solve this equation. I could find the solutions for this perfect square trinomial because as we saw, this is x plus 7 squared, right? Equals 4. And now that I have a perfect square here, how do I know it's a perfect square? It's squared. If it's squared, it's definitely a perfect square, right? I can take the square root of both sides. And when I take the square root of something squared, I'm just left with this thing that's being squared. So x plus 7 equals plus or minus. What is the square root of 4? This will be the easiest question I ask you all day today. 2, right? So we have plus or minus 2. And now we can solve, right? We're just going to subtract 7 from both sides. And we wind up with x equals, well, I have minus 7 plus 2, right? Minus 7 plus 2 is negative 5. Negative 7 minus 2 is negative 9. These are my two solutions, right? Think about that. We have two solutions. We're talking about quadratics. Does anybody, I will give some extra credit points to whoever can answer this problem. Does anybody know what those solutions represent? Coordinates, that's a start. What coordinates? Well, that's what a coordinate is, but what specifically do they represent? What coordinates do they specifically represent? We've talked about this before with solutions to quadratic equations, and that's what we're doing, right? These are quadratic. Yes, they are points. That's what a coordinate is. But what specific points do they represent? You will get partial credit for that because you did come up with the fact that there's points. But yeah, you did say that. That's what a point is, right? It's an x and y value. But these are very specific points. All right. Anybody else chiming in with this one? That's okay, Jeremiah. It's okay to have no clue. I'm sure you're not alone. You don't see a bunch of other people jumping in on the answer. We talked about it before when we were talking about what we were looking for with quadratics, right? And when we graph them, they're always in that U shape, that parabola shape. And our solutions are always these points where we cross the x-axis, right?
That's when you draw the little like curve thing.
The parabola.
How do we know like is the y just double check the y-intercept is how much it has to go like up or down, right?
Well, no, the intercepts are where they cross the axis. So this is the x-axis and this is the y-axis. So any point on the x-axis is an x-intercept. They are also the solutions to our quadratic equations or the roots or zeros. We call them all sorts of things. But with quadratic equations, we're looking for points on the x-axis. Intercepts, they can also be called. Our y-intercepts are where it's crossing the y-axis.
Yeah, that's what I meant. Maybe my brain's jumping ahead, but I know like when you draw like the graph itself, you have to have the y-axis in order to like.
Well, y actually doesn't make much of a difference in terms of how to graph it. It does tell us where to put the points, but the y-intercept itself doesn't play a huge part in quadratics. Because we're more concerned with where the x is, what's on the x-axis when y equals 0, right? Our solutions. And then we're concerned with the minimum or the maximum depending on what we call the vertex point. So instead of that, we use what we call an axis of symmetry, which is that line that divides this parabola in half, so that when you fold it on that line, they match up on both sides, which can sometimes be the y-axis, but not always. So yes, the y-intercept, when we're doing lines themselves, very key element in solving equations, which might be where you're thinking about, because it's huge when we're talking about lines, when we're talking about linear math. But now we're moving away from linear into curves, into higher degree equations, and we tend to use the x-axis more. That's all. Because that'll show us where the turns are. So that's what we were getting at with the solutions, is that they're just those points on that x-axis where this parabola is going to cross. So you will almost always have two solutions. The only time you don't is, say, if the vertex sits right on the line, right? In which case you would only have one point. Let's do some more. Well, I'm not going to do any more examples of perfect square trinomials because we do have to get into the completing the square portion, since that's what the lesson is on. I am going to start with writing out some steps for it. Will they make sense? Probably not right away, right? Because, you got to see them in action first. But I always like to start with steps where I can. So, steps for completing the square. Shaylin, you could probably already see them up on the board there, because I taught this class right before you came in. So, steps for completing the square. The first one is we are going to rewrite whatever problem we're getting as ax squared plus bx equals c. What it's saying there is anything that isn't an x or an x squared term needs to go to the other side of the equal sign. Anything that is an x or x squared term needs to be on the left. Anything that doesn't have an x or an x squared next to it needs to be on the right. That's all that means. Number 2, divide. I hate this new whiteboard, man. Both sides by a term. That means if I have ax squared plus bx equals c, right? And my a is anything other than 1, if I have anything other than just an x squared here, I need to divide each piece by whatever that a is. That's all that means. 3, we're going to complete the square. Man, there's a lag, so I cannot see what I'm writing. It's driving me crazy. Hate my new whiteboard, man. I don't know if it's because I updated the computer or because I switched over to Google Chrome, but I don't like it. Complete the square by taking half of b term squaring and adding to both sides of the equation. That looks ugly. It kind of is. It's the ugliest part of the whole thing. But it is okay. I was just going through regular Google. When I switched to Chrome, all of my life got ruined. Take square root of both sides. And that's it, right? That gives us our solutions. Reduce. We'll put reduce down there because, right, we want to definitely reduce. Is this ugly? Yes, absolutely. It looks ugly. I'm going to erase this little part right here because I want to do the first problem right here where you can see the steps before I move away from them. So I'm going to start with, if I have, where'd my thing go? My first example I'm going to go with is if I have x squared minus 18x plus 56 equals 0. All right, so it says that my first step is to rewrite as ax squared plus bx equals c. So the only thing I want on this left side here, right, on this side, is this, right? I'm going to move this 56 over by just subtracting it from both sides. And I can rewrite the problem as x squared minus 18x. I'm going to leave a little space here. I always like to do that when I'm completing the square, and you will see why. Equals negative 56. Right? So we're done with part 1. Part 2, step 2, says that we're going to divide both sides by the a term. But we don't have to do that when the a term is 1. If I have it written as x squared and there's nothing in front of that x squared, it means that there's like this imaginary 1 there. And if I divide everything by 1, it doesn't change anything, right? X squared divided by 1 is just x squared. Minus 18x divided by 1 is just minus 18x. Negative 56 divided by 1 is just negative 56. It doesn't change anything. So even if I did go through the motions of dividing both sides by a, it's not going to change anything. It's going to leave us with the same equation. So we can move on from that one. And we're going over to step 3. And step 3 is to complete the square by taking half of our b term, squaring it, and adding it to both sides of the equation. Our b term is always whatever is in front of our x value, right? We are taking our b term, we'll do it right down here, b over 2 squared, right? We're taking whatever b is, we're dividing it by 2, right? That'll give us half of it, and then we're going to square the outcome. So we're taking our b term, which is negative 18, we are dividing it by 2, and then we're going to square it. Well, what is negative 18 divided by 2? Negative 9. So I'm going to have negative 9, and I'm going to square it. That's the same as saying negative 9 times negative 9. Am I right? So that's just positive 81. So we did the main piece. We found out what we're doing. We're completing the square by taking half of the b term, squaring it, then we're going to add whatever we get to both sides. So this would be plus 81. Hopefully that comes out. I don't know. I wrote it 6 seconds ago and it just showed up. Plus 81. What we created here on this side is a perfect square trinomial. It's the whole reason we do it. So I know that I can write this. In this case, it's going to be x minus, it doesn't look like a x, x minus. The reason it's minus is because this right here is minus. So it's x minus whatever the square root of this is. In this case, that's 9 squared. Equals, well, 56, negative 56 plus 81 is just 25, which is conveniently a perfect square. Right? So we've done this now. We've taken, we've added it you know what I forgot? I forgot a little step in here is factor. Factor the sides, right? Factor both sides. Or factor just factor between those two, right? That's what this is, right? We just factored it. And so now we can take the square root of both sides. Boom. Well, the square root of something squared will just leave us what's within those parentheses. So I've got x minus 9 equals plus or minus the square root of 25, which is just 5, right? So we need to know what x equals, and we're going to find that by adding 9 to both sides. And this is where we're going to find our two solutions, right? Adding 9 to both sides. Boy, the lag on this is so bad today. It's making me a little insane. So here I'm going to get x equals, well, I have positive 9 plus 5, that's 14. Then I have positive 9 minus 5, that is 4. These are my solutions to this quadratic equation, right? Are we going to do more of this? Heck yeah, we're going to do like 2 more examples. Because I want you to see one where we actually have to divide the a, and then I want you to see one where we have everything together and we get an ugly fraction and we have to find a common denominator because I like it ugly. Was that Happy Halloween because I used orange and purple, Jeremiah, together? Because those are kind of Halloween colors. So let's look at, what if I have, for a new example, man, the lag is so bad today. Two x squared minus 16x equals negative 30. So it's already set up in the form that we want. We don't need to move our constant over, right? Because the negative 30 is on this side. All we have are x squared and x terms on our left-hand side, which is what we want, right? Our next step would be to divide everything by our a term, right? If it is not 1. And in this case, it is not 1, right? In this case, what is in front of our x squared is 2, so we have to divide every piece by 2, right? 2 divided by 2, well, that's just going to give me x squared. It's the main reason that we do it. Negative 16 divided by 2, well, that's just negative 8x equals negative 30 divided by 2, well, that's just negative 15. So we're there now, right? So now we've got to do the part where we're completing the square, where we have to take our b term, divide it by 2, and then square it. What is my b term? What is b on this one? Sergio for the win. Well, he had it. Then he went and threw the x in. It's always that coefficient in front of your x or in front of your x squared, right? A is what's in front of the x squared. B is what's in front of the x, right? So negative 8, I see all those negative 8s popping up. So if I have negative 8 and I divide it by 2 and I square it, well, negative 8 divided by 2 is just negative 4. Looks like negative y, but it's negative 4 squared. Negative 4 squared is just 16, right? And so what I'm going to do is I'm going to add 16 to each side. Gosh, this is driving me crazy. I've got to figure this stupid board out today. And so I'm going to add 16 here. Can you guys kind of see how bad it's lagging, or can you not tell because it's not your hand that's on the board? Like I write it and then I've got to wait for it to actually show up. Yeah, it's really weird. So we've created our perfect square trinomial here, right? We know that it'll play out this way because we designed it as such. So we could write this as x. This is our b term is minus, so it's x minus. The square root of 16 is 4, so it's x minus 4. Will the square show up? I wrote it. There we go. Man, that takes forever. Before we left last week, it wasn't this bad. It is way worse today than it had been before. I don't know why the lag is so bad. I don't know what I'm going to do about that. I have minus 15 plus 16, which is just 1. That's kind of convenient because yeah, it really did. Maybe it's just like the rest of us. It's taken a while to wake up. So we have our perfect square trinomial. We've got all our math done. All we have to do is take the square root of both sides, right? Here we're going to be left with x minus 4 equals, well, the square root of 1 is plus or minus 1. So that's super convenient. Right here, we've got x minus 4 equals. We don't care what x minus 4 equals. We want to know what x equals. So we're just going to add that 4 to both sides so that we can have x isolated. And we get 4 plus 1, which is 5. And we get 4 minus 1, which is 3. Those are our solutions, right? X equals 2 things. It equals 5, and it equals 3. Good? You good? I'm going to do one more problem. Do I have time? Yeah, we got 10 minutes. This will be the hardest problem we do. It will be the hardest problem that you get, right? You won't have anything hard. Oh, I was trying to find the hand that makes me slide that up, but no. Just wants to leave dots. Why? Where's the thing that makes me... Oh, this is driving me crazy. Maybe if I do it with a cursor, it'll... There we go. Wasn't letting me slide the page up. I'm telling you, this new whiteboard is going to be the death of me. Maybe that's dramatic. It probably won't kill me. It probably won't be the death of me. It will be my nemesis, though. Like, I'm going to be in the market for a new whiteboard if I can't get this working a little bit better, because this is crazy. Like, I finished that X a long time ago, and it just popped up. So this right here, hardest problem that you will get. But I want you to see examples of it. So I'm going to do this one. Even I hate doing problems like this, and I love math, right? So if you look at this and you go, Miss Hoy, I hate this, you should think twice about giving us problems like this. No, I shouldn't. I love problems like this in the sense that it makes you practice fractions, which I think most of you are weak on. And I don't even think it's entirely your fault. I just don't think they spend enough time teaching them when you guys are younger to fully get them. They kind of rush through and you guys kind of never get that full grasp of them. So first step, we talked about it before. It said our first step was to rewrite the problem so that only the x's are on this side. So we're just going to subtract 8 from both sides and then rewrite the problem as 3x squared, hopefully, plus 10x. Hopefully this will catch up with me because I've been writing this whole thing. Okay, it did. Equals negative 8. Right? This is so wild. Next, it says that we're supposed to divide by our a term, right? If the a term isn't 1, then we have to divide everything by a. So we're going to divide this by our a, which is 3, this by our a, which is 3, and this by our a, which is 3. But notice that leaves me with some fractions. This leaves me with x squared, which is what we want, plus 10 thirds x equals negative 8 thirds. Right? So we've got some ugliness happening here, right? Because now our next step, ow, my hip did not like that. Our next step is to take our b term and divide it in half, right? And then square it. We have our b over 2 squared. And in this case, our b happens to be 10 over 3 now that we're taking half of, and square. How do you guys handle that problem? You have 10 over 3 divided by 2. Ultimately, this is the same as saying, yes, you do the change flip method. This is technically 2 over 1, right? So what we're doing is we're going to take that 10 thirds and we're going to multiply it times the reverse of this, right? The reciprocal of this, which is 1/2. Well, it was 1/2. It just didn't want to write that whole 2. 10 times 1 is just 10. 3 times 2 is 6. So we have 10/6. Can I keep it as 10/6? No. That's a reducible fraction, right? Everything there is divisible by 2. So we have 5 thirds. So ultimately what we're looking at here is 5 thirds squared. I hate it when it only gives me part of the number that it is. 5 thirds, well, 5 squared is 25. And 3 squared is 9. So we have 25 ninths. And that is what we are going to add to both sides. Here we are going to add 25 ninths. And here we are going to add 25 ninths. It's like sometimes it catches up, sometimes it doesn't, and I have to go fill in the blanks. So here we have some ugly, like this side is nice, right? This side I could write pretty easy. I could go, this is now going to be x plus the square root of each of these, which is 5 thirds, right? Squared. But we have to deal with this mess right here, which requires that we find a common denominator so that we can add them together. The only time you ever need a common denominator is when you are adding or subtracting fractions. That is it. Lucky for us, this is a fairly easy common denominator to find, right? Because 3 times 3 equals 9, right? So I can take my minus 8 thirds and multiply that times 3 over 3. Why would I use 3 over 3? What is 3 over 3? Right, Sergio, it's 1. Anything over itself is 1. 8 million over 8 million, still 1. X over X, 1. What happens when I multiply something times 1? What's 4 times 1? Yeah, everything stays the same. So the whole idea when we're finding common denominators, the reason that we multiply something over itself, like if I know 3 times 3 will equal 9, I multiply by 3 over 3 because we're not changing the value. We're just multiplying times 1, right? We're changing the way it looks, but we're not changing the value, right? So when I get this, I'm left with negative 24 over 9, right? And when I add that to this 25 over 9 that I have over here, I'm left with just 1/9, right? And so that is what this is equal to, 1/9, once I find that common denominator. Now I can go ahead and take the square root of both sides. Told you this would be the hardest one, but I wanted you to have an example of the hardest kind that you're going to come across, right? So I'm taking the square root of both sides. This just leaves me with x plus 5/3. I have to wait and make sure it shows up. Equals plus or minus. The whole plus didn't want to show up. Well, the square root of 1/9 is like saying the square root of 1, which is 1, over the square root of 9, which is 3, right? And then we just have to go ahead and solve. We're just subtracting. I'm moving because the bell just rang and I don't want anyone to be late to the next class. 5/3. And then we just add them together, right? We've got x equals, well, minus 5/3 plus 1/3. That's like saying minus 5 plus 1. Well, that's minus 4/3. And then we have minus 5 minus 3. Well, that's minus, I'm sorry. I don't know why I was saying that. Minus 5 plus 1 is negative 4/3. Minus 5 minus 1 is negative 6/3, right? Which is the same as saying negative 2. So your two solutions, negative 2, negative 4/3. You are all free. I know that was a long lesson. I apologize for it. I will post this one, but if my other one comes out better, like if my whiteboard's working better on the next one, I will replace it with the next one. All right. I will let you guys go.